Okay, so today on the lecture of balancing of rotating masses, we are using the graphical method. We are going to see the balancing of several rotating masses in single plane, which means in a shaft, when you are going to take a shaft, this shaft which is going to rotate at an RPM, we are going to consider a plane over here. Let me consider this plane to be as A. In this plane A, there are n number of masses. So let me take M1 R1 and M2 R2. From this geometric center M2 R2 and M3 R3. These masses are rotating with respect to this geometric center, which are all acting in the same plane. These forces M1, M2, M3 are contributing towards the out of balance force, that is nothing but a disturbing force, that is centrifugal force. This disturbing force needs to be nullified such that the system needs to be brought to a balanced condition. In order to bring that system into a balanced condition, we need to bring a mass at a certain specified location along this plane. Since these masses are acting in a coplanar condition, we have to bring a mass that at a certain radial distance that will tend to bring the overall system into a balanced condition. So that's what we are going to see. In this problem, I will read out the question. This problem, there are said a rigid rotor has its unbalance in one plane and can be considered to consist of three masses. M1 is equal to 5 kg, M1 is equal to 5 kg and M2 is equal to 8 kg and M3 is equal to 3 kg. Sorry, M2 is equal to 3 kg and M3 is equal to 8 kg and M4 they are not given. So M4 is not given over here. And then they are said the M2 is located as 165 degree counterclockwise from M1 and M3 is equal to 85 degree clockwise from M1, they are saying. So what we are doing, we are going to take everything in terms of counterclockwise direction from the reference M1. So in order to that, what we are going to do, we are going to take in terms of 360 degree a plane to overall angle possessed by a plane is 360 degree. In 360 minus 85, I am going to take counterclockwise from M1, it's going to be 275 degree. Okay. So and then they have said the balancing mass is possessing a radial distance of RB is equal to 10 centimeter, which is equal to 0.1 meter. And they also that have given the radial distance at which the several masses M1, M2, M3 are placed. That is R1 is equal to 20, R2 8 and R3 is 14 centimeter. I brought out everything in terms of meter. And they have said the balancing mass is acting at a radial distance of RB is equal to 10 centimeter, which is equal to 0.1 meter. And then what they asked us to find, they have said determine the mass of the balancing mass, which will contribute to the nullifying the effect caused by the unbalanced forces, and then theta b. At what location you have to specify a mass, and they are also given with respect to the value or with respect to the mass b as well as theta b. There is a balancing mass which is located at a distance of RB is equal to 0.1 meter. So before solving, how we can able to approach these kind of problems? First of all, we need to solve this problem in terms of, first we need to find the centrifugal force, that is out of balance force that has been created by these different forces, that is here FC1, FC2, FC3, that is contributed by mass M1, M2, M3, which is acting at a certain distance from your center of geometric center of your shaft. So that we have obtained MC1 is equal to M1 into R1 is equal to 1 kg meter and FC3 is equal to M2 into R2 is equal to 0.24 kg meter, FC3 is equal to M3 into R3 is equal to 1.12 kg meter. And since this is a graphical method, we need to, second approach will be, step 2 will be here, we need to go with your space diagram. Space diagram, we need to take one of the masses to be in a reference plane, and that we are going to take to be as our mass M1. So what I am going to do, with respect to O, a point O we are going to take, and this is taking to be as a reference plane M1, and we are totally concentrating on only the orientation of the masses and not about the dimensions possessed by the mass. That is your R1, R2, R3. You need to stick on to the only to the orientation process by your M1, M2 and M3. So M1 I am going to take at a reference plane. It is going to be at 0 degree, and then in the problem that I have said, M2 is acting at 165 degree counterclockwise from M1. So from M1 I am going to, with the help of the protractor, I am going to draw M2 which is acting at an angle of counter 165 degree. And then from the problem, the given data, I have solved this problem M3 is equal to 85 degree, which is clockwise from M1. I solved this, solve this problem in such a way, it is acting counterclockwise direction 275 degree. So from here, I am going to take my mass M3, which is acting at counterclockwise direction from with respect to M1 is going to be 275 degree. So that's what that's with the respect to the space diagram, and next we need to attain the value. Since this is a graphical approach, we need to move on to the we are in a position to determine the magnitude as well as the direction possessed by the balancing mass, that is your FB. We are very much concentrate about our FB. In order to determine our FB, we know very well, to determine a force through a graphical approach, we need to go for polygon law of forces only. So such that the resultant force, that is the closing vector, will tends to provide us the system to be in balanced condition. That will be given by a FB. Now we will see how we are going to solve that problem. Okay, problem that is a force polygon. So we are going to construct the force polygon of this the overall system of forces. With respect to the space diagram, what I am going to do, we are going to construct the force polygon, that is polygon force vector. So step 1 is your centrifugal force. In the centrifugal force, we have obtained the values of, from the step 1 we have obtained the value of FC1, FC2 and FC3. So from here we are going to construct that with this value as well as the orientation of the masses, we are going to construct the force polygon. So with respect to that, I am going to take my scale to be as 1 centimeter is equal to 0.2 kg meter. So such that my 1 kg meter, when I am going to divide by 0.2, I will be getting the value in terms of 1 centimeter. So I am going to first consider my FC1. So I am going to take O. So how I am going to do, with respect to the reference space diagram, I am going to draw a parallel line. So O is here and M1 is over here. And with respect to the value of whatever has been possessed by the force vector FC1, that is with this multiplied by the scale, that is divided by the scale value, that is 1 divided by 0.2, I think we will be getting in terms of 5 centimeter, I think so. So from here I am going to draw, so since it is going exerted outside, it is moving outside in a positive vector, in a positive quantity. So I am going to take OA, which is going to be parallel to with respect to your M1. So that is going to be a FC1 vector. Okay, and then I am going to construct with respect to the FC2 value with divided by the scale value. I am going to take parallelly with respect to here, and I am going to draw my AB. So this is going to give me my FC2. Okay, and then the mass, that's out of balance exerted by a mass M3. So parallelly with respect to here, I am going to draw a line parallelly with respect to a mass with respect to the space diagram. That is the value that has been obtained by my force vector, that is 1.12 kg meter, and I divided by 0.2, I will be getting in terms of centimeter scale. So that will tends to give you OC. So this is nothing but is a FC3. Okay, and then the closing side of this vector will tends to give us the balanced force vector. So that means the condition, the system is to be totally in terms of balanced condition. So that will be acting in an opposite direction. So such that this will be giving us FCB, that is your centrifugal force that has been created by the balanced force, balanced mass, which will tends to provide us the nullifying effect that has been contributed by the out of balance masses, that is out of balance forces. So with respect to that, I am getting that FCB is equal to vector OC. So vector OC with respect to the value of when you are going to multiply with respect to the 0.2, I will be getting the value in terms of 1.1 centimeter, that value to be as 1.4 kg meter. Okay, so we know that FCB is equal to what? FCB is equal to MB into RB. We know that in our problem, our RB is given to be as 0.1 meter. So from there, that is MB into 0.1, I am going to get my MB is equal to 14 kg. That is the mass possessed by the balancing mass. That is the balancing mass. So this is the one of the thing that has been asked in this problem, and then they have asked us to determine the location of the mass. We need to locate it in the plane. So with respect to the force vector FCB, we need to take this force towards your space diagram. So since this is acting towards the downward direction, we need to bring towards the downward vector. So if I am going to take this from here, this is so you have to take this parallel over here. So with respect to the origin, you have to bring your force vector over here. So this force vector will be your FCB. Opposite to the force vector, along this line of action, we will be having along this same line, we will be having our balancing mass MB, which will be acting. So you have to find it with respect to mass M1. That will be equal to theta B will be getting in terms of 130 degree. So that is so you have to be very much careful in terms of your you have to locate your mass MB. With respect to the force vector, we will be drawing the resultant force in our space diagram at the outward condition. Since it is acting downwards, we have to take your resultant force along the downward direction from respect to O point. And then along the same line of action, you have to extend this line. You will be getting your mass MV, and then with respect to M1, you have to determine your theta B, which will be equal to 130 degree. Okay. So this is how we need to solve this problem. I am saying again, the balancing of several rotating mass in single plane is nothing but first step we need to find the centrifugal forces that has been contributed by the out of balance masses, and then from there you need to move on to the space diagram to place the different masses located at different location with respect to a reference plane. And then you, with respect to a force polygon, with the sticking on to the scale value of whatever your wish, we are constructing a force polygon, and the closing side of the force polygon will tends to give us the balancing mass force vector. That balancing mass force vector will be equal to vector that has been possessed. We know that FCB is equal to MB into RB. We know the centrifugal force is equal to product of mass into the radial distance. So MB is equal to RB, which is equal to MB into 0.1. So MB is equal to 14 kg we are getting. And then what we need to do, we need to specify the location of the balancing mass. So we are specifying the location of the balancing with respect to the force vector. We are going to, since it is moving outward, so we are giving okay. So we are placing over here, and along that line of action, we are placing our mass MV that is measured to be as from M1 to be as theta B is equal to 130 degree. So this is how we have to solve this problem. In terms, it has been asked balancing of several rotating masses in a single plane. Okay, thank you.